Hi, I'm Dan Gibney, and today I will be discussing with you recent results by Chirag Jain, Sharma Thenkachan, and me on the problem of collinear chaining. Sequence alignment is one of the most fundamental problems in computational biology. Unfortunately, computing an optimal sequence alignment is not as easy as we might like. Even when we look at only two sequences, doing significantly better than the quadratic time dynamic programming algorithm for edit distance seems hard. So we turn to heuristics, which is where collinear chaining comes in. In the version of collinear chaining we will consider here, we start with a pre-computed collection of exact matches called anchors. Our aim is to find a collection of anchors that we wish to keep. Then these anchors can be used as a sort of coarse-grained sequence alignment. Then later this coarse-grained sequence alignment can be further extended as needed using seed extension heuristics. So here's an illustration of a collection of anchors representing exact matches, shown as rectangles. Now the aim is to find an optimal subset of these anchors subject to some cost function. And one possible example is given here with these two anchors. Techniques like this are used for long-read mappers like minimap2, minigraph, or winnowmap2, and also for genetic alignment tools like Nusimer, Clasp, and Coconut. There are different algorithms for this problem that depend on the cost function that we're working with. For cost functions where the overlap is not allowed, where there's no overlap allowed between anchors, there exists an algorithm running in time big O n log log n time. For cost functions where overlap between anchors is allowed, but the gap between anchors is not considered in the cost function, there exists an algorithm running in time big O n log squared n. Now, prior to our work, there was no algorithm for both overlap and gap, cost being allowed in the function, the cost function. And that's a problem because arguably having both is a more realistic model. There's no reason to assume that in an optimal alignment, the anchors would be non-overlapping. And also not taking into account large gaps between the anchors seems unlikely to produce something close to an optimal alignment. So to address this issue, let's discuss the cost function which we can use that accounts for both of these. We'll start with a bit of notation here. Each anchor has 4 associated values. 2 are for the first string and 2 are for the second. We say an anchor I dash is less than I under weak precedence if I dash dot A is less or equal to I dot A, and I dash dot C is less or equal to I dot C. We say an anchor I dash is less than I under strong precedence if I dash dot A is less or equal to I dot A, I dash dot B is less or equal to I dot B, I dash dot C is less or equal to I dot C, and I dash D is less or equal to I dot D. The gap cost between anchor I dash and I is going to be the larger of the two gaps occurring between the two anchors, written formally here in this first line. The overlap cost between anchor I dash and I is going to be the absolute difference in overlap between the two anchors, written here in the second part. And the cost of the ordered set of anchors is going to be defined as the sum of the gap and overlap costs taken between adjacent anchors in the ordered sequence. So we can provide an algorithm that solves the collinear chaining problem with overlap and gap costs in time big O tilde n. Here this big O tilde n hides polylogarithmic factors. And here are some special cases where we can actually give the logarithmic factors. For chains with fixed length anchors, we can solve this problem in big O n log squared n time. For chains under weak precedence, not necessarily fixed length anchors, we can solve the problem in big O n log cubed n time. And for chains under strict precedence, we can solve the problem in big O n log to the 4n time. Okay, our second main result is proving the equivalence between collinear chaining under the cost function that we use and a generalized form of edit distance we call anchored edit distance. In this generalized version of edit distance, we have that exact matches that are not supported by an anchor will incur a unit cost. Now this results in the dynamic programming solution written here. The only difference between this and the usual edit distance dynamic programming is that the x variable written here is 0 only when both an exact match occurs and that match is supported by an anchor. This illustration of an alignment shows exact matches as solid edges, substitutions as dotted edges, and deletions as x's. And the key here is that any solid edge is always going to be supported by an anchor in anchored edit distance. Now our work proves the following equivalences. For a fixed set of anchors, the following quantities are equal: the optimal anchored edit distance, the optimal collinear chaining cost under strict precedence, and the optimal collinear chaining cost under weak precedence. This makes the first direct theoretical connection that we're aware of between collinear chaining and edit distance.